Thanks for the reminder. Okay. Okay. Okay, so last week we started with calculating cell. Sorry. So last week we started with calculating cell EMFs from standard potential. We treated the examples and yes. So this was where we were. We treated the examples and then the answer we got from the last one was 1.20. So on this slide, we asked, how would we write and draw the cell we just did in short notation? This is straightforward. The answer is right there on the slide. You have your cadmium on the left, and the left represents the what? The left represents the what? Is it the anode or the cathode?
Anode.
The anode.
Anode.
And what happens in the anode?
Oxidation.
Fantastic. Oxidation. So you have your cadmium, oxidized to cadmium 2+. You have your salt bridge, which is shown with a double slash, and then your silver in its oxidized form being reduced to silver. And because they are in different phase, you have a single slash separating it. And here is the diagram. Okay, I don't think I would ask you for, maybe, you never can tell. I may ask you just something simple like this. Draw the cell and write the cell notation. So I want you to quickly solve this. I want you to write the cell notation for this. Okay, I hope you can see this. I want you to write the cell notation for zinc solid going to zinc 2+ plus 2 electrons. And then Fe3+ plus electron to, okay, it's a reversible reaction actually, but I can just let it be like that, Fe2+. So, for just so you know, sometimes people leave out the state, but anytime the state is not given, I want you to know that once you see that they are in ionic form, they are in what state?
Solid.
Ionic form.
Aqueous.
Aqueous. When they're in ionic form, they are in aqueous state. And when they are in their zero state form, it's most likely metals. So you know that zinc, you know iron, the transition metal, and then it can be sodium, it can be magnesium. Just keep it in mind, just in case the states are not stated. The moment you see that they are in their ionic form, they are most likely aqueous. And then, of course, when you have them in their free state, they exist as metal, either a group 1, group 2 metal, or a transition state metal. All right, so I want you to write the cell notation for this. The first thing I want you to do is to identify. Let me number it, equation 1 and 2. Which one is the anode and which one is the cathode? Equation 1 or 2, which one is the anode?
I think it's the anode.
Okay. And then the cathode is what?
Equation 2.
Equation 2, obviously. So what's the cell notation?
Zn
Zn
slash
yes, I'm waiting.
Zn slash
I'm with you.
Zn Zn slash
slash
Zn2
Zn2 plus double
then the
slash
salt bridge Fe3 plus slash Fe2 plus.
eh?
Okay, this is what somebody is saying, slash Fe2 plus. Thank you. Who has a different answer? Who has a different answer? Do you all agree with this?
Yes, ma.
But the electrons, they're not balanced.
The electrons are not balanced.
No, ma.
How do you mean? The only thing you are writing is the cell notation. You are not balancing the equation. You are not doing anything with the reduction potential. When we get to that, we can look at that. But for now, we just want you to write, okay, I can see somebody's Akano on Olapo. So your response is the same as what we have on the board. Does anybody have a different opinion from this?
Yes, ma.
Please, Chuku, can I hear you?
Zn
Yeah.
slash Zn2 plus, then the salt bridge, then Fe3 plus, comma,
Thank
Fe2
you.
plus.
Thank you. That's exactly what I wanted to hear. Why are you saying this is comma? Why did you use comma?
Because they are in the same.
Exactly, because they are
Because
in
in
the
the
same
state.
exactly, because they are in the same state. So you expect this to be comma. Assuming 2, so let's say 2 now. So let's say equation 1 is zinc as it is on the board. So zinc 2 plus 2 electron. And then you have say Ag plus electron to Ag. This is aqueous. This is aqueous. What would be the cell notation? Which is the anode, which is the cathode, and what would be the cell notation? You need, okay, for those of you who do not understand what we're doing, for you to be able to write the cell notation, remember that when we started the class, we said that the cell notation is taken from the left. So in an electrochemical cell, you have 2 half cells. One is on the left, one is on the right. Of course, when you have 2 beakers, let's assume this marker is a beaker, and then this duster is a beaker. You have the 2 of them placed like this, and you have solution and the electrodes in them. One is definitely on the left and the other is on the right. So the one on the left is our anode and the one on the right is our cathode. Now you're going to now write it according to what electrode you have in this one, which is on the left, which is your anode. So you move from the left to the right. When you are writing your cell notation, you move from the left to the right. You move from the anode to the cathode. So that's why you need to identify which of the 2 equations represents the anode and the one that represents the cathode. And how do you represent which of the equation represent the anode or cathode? The first thing you need to know is what is happening in the half cells. Now we said that in the anode, what you have in the anode is electron is moving out from the anode to the cathode. If electron is moving out of the anode to the cathode, it means that oxidation is happening at the anode, and at the cathode where the electrons are being deposited, there's going to be reduction there. Remember that your electrons are coming with negative charge, so it's reduction wherever it is they are going to. So here we can see that zinc is being oxidized to zinc 2 plus. So we can say this is our anode, which is the equation on the left, because oxidation is happening in this reaction here. And while here you can see your Ag plus, your silver is moving from +1 to 0 state. So we can say reduction is happening here, which is the cathode. So that's how we are able to tell that this is anode and this is cathode. And for you to write the cell notation, just write all these participants that are there. So what are the participants in your anode? what you have is zinc. So I'm waiting for everyone to tell me what the cell notation is now. The cell notation, please.
Zn
Zn.
slash Zn2 plus.
So you just follow that way, ignoring the electrons. You are going to use slash at this point because this is in solid phase and this is in aqueous phase. That's why we're using slash. And then the next thing is what?
The salt bridge.
The salt bridge, which is represented by a double slash. There's a salt bridge usually between the anode and the cathode. So then the next thing is what?
Ag plus.
Ag plus
Slash Ag.
slash Ag. So now you can see the difference between this and this. These are in the same phase, aqueous. So it's separated with a comma, but these are in different phase, solid and aqueous. So that's why you are having a single slash separating them. Do I have any other example? Okay, so as we move on, do you have a question?
We are not seeing the down part of the board.
Can you see
So
it now?
to do the camera.
Oh,
No.
sorry.
Okay. Yes.
So it's okay
Yes,
now.
thank you. Yeah.
All right. So that's that with the cell notation. Can I move on?
Yes, ma.
Yes, ma'am.
All right. Let me see if I can find, I think I have another example that I wrote somewhere. All right, so let's move on.
Ma, hello, ma.
Yes, please.
I have a question.
Okay. Please shoot.
Okay, if we were given Zn2 plus 2 electrons going to N, and they gave us like an E naught value, and we are also giving Ag plus an E and an electron to Ag. If we want to change the Zn to the oxidation form, we will also change the value on the E naught.
Sorry, please, can you take the question again? I think I understand what you're asking, but I want to be sure what you asked.
Okay, for this last example that you gave us, that zinc is going undergoing oxidation. What if it was in the reverse state? Although we cannot have two electrons on the same side, it's meant to be opposite. If we want to change it, are we going to also change the E naught value? Maybe if it was a negative, will it become positive?
Well, that is another question entirely from what we just discussed on the board. That question you're asking is based on the last example we solved in the class the last time. So I would try not to discuss it now, because for this particular question, what you're just asked to do is to write the cell notation. It's just write the cell notation. Now, if you are asked to calculate the EMF of a cell, which was where we stopped the last time, you would either rearrange it. So it can, like this now, this example I gave you now is written as an oxidation and a reduction equation. So if it is given, if the question is given this way, you can use it like that, balance the equation as you would a redox reaction. And then for the first one, which is written as an oxidation, you would reverse the E naught value. If it is positive, it becomes negative. If it was negative, it becomes positive because it is now in oxidation. Meanwhile, the table of values you have is reduction potential. We are going to really treat that extensively so that you understand. And that's one of the reasons I don't really want to talk about it now, because it's not before us right now, but it's part of this example. Do you understand? So let me just try and take it. And I want everyone to follow me. If you don't have a note, get a note and write, because sometimes it can become confusing. You know, even me trying to teach and planning for the class, I realized that I can't just use slide, because when you use slide, it has a way of restricting you. We also need to, you know, to support it with a board. I had to go and look for a board that I can use. So please, in your best interest, get a note and write these things and read, because we are really behind schedule. This particular aspect that I'm teaching, we'll still touch it again after we are done. You know, we started with derivation of the electrical parts and the chemical parts. So we talk of electrical potential and chemical potential when we were on campus, the very first class we had. We are still going to get back there and we'll talk about standard hydrogen electrode. And when we talk about all the electrodes, we'll still come back to calculating EMF. So please follow me, because by the time we get to that point, I'm just going to brush through it because we've discussed it extensively from the beginning. All right, so we have written the cell. Can you still see my slide?
Yes, ma'am.
Oh, good.
Yes,
Okay, so we have written the cell notation, and let me put on my pointer. We have written the cell notation, and here is the cell. So if you're asked the question, you're asked to write cell notation. This is what they mean. This is the cell notation. When you have been given the oxidation and the reduction reaction, you should be able to allocate which is going to anode, which is going to cathode. Like I said, oxidation takes place in the anode. So the moment you see oxidation reaction comes first. I don't know why there's an echo. I can get a feedback from here. I don't know why. Okay, so now here's a problem to consider. A minute, please. Sorry. So here is a problem to consider. It says calculate the standard EMF cell. I don't know where this feedback is coming from. Please, can you all mute for now?
That's why there's an echo.
Because they are not all muted.
Yes. Mary Damilola is not muted.
I think it's better now. Okay. All right. So calculate the standard EMF cell for the following cell at 25 degrees centigrade. So the moment they say standard EMF, you know that you can use your standard reduction potential to calculate. So what do you have? The equation has been given. And remember the formula, we said let me take it back to that part of the slide. We said you can either do it one of two ways. So here, you can either say your E naught is your standard reduction potential, that's the reaction of the cathode, minus the reduction potential at the anode. Or you can say your reduction potential of the reduction, or you say the oxidation plus the oxidation potential of the oxidation reaction. If you use this first equation, then you have to do that reverse and reverse and reverse. That was it Mary that was asking the question earlier? Somebody asked that question earlier. So if you decide to use this equation, then it means that when you have identified your oxidation, you will need to reverse, as in to multiply that value by negative. You will need to multiply the value of the standard reduction potential by negative for you to get it as an oxidation potential because this says oxidation potential. But if you want to use this equation, which is the reduction potential of the cathode minus the reduction potential of the anode, then you don't have to reverse anything. All you need to do is to make sure that you identify which is the reduction and which is the oxidation. And we know that your oxidation is in the anode. We know that your oxidation takes place in the anode and your reduction takes place in the cathode. So when we say reduction minus oxidation, it means that your right minus left. So your E naught value of your right minus the E naught value of the left. What you have on your right is the cathode, and what you have on your left is the oxidation, which is the anode. So let me go to the current example and the current classwork, and let's solve this together. So here is the equation. The reduction half reactions and standard potentials are given. So you have here, everything has been written the same way. How do we tell which is oxidation and which is reduction? Can anyone tell me which is oxidation?
Aluminium.
God bless you. Aluminium is the oxidation, and you would have seen that from the cell notation. We know that from the cell notation, we take our anode first, then our reduction follows. But from this equation that is given, both of them are written as what?
Oxidation.
Reduction.
What?
As reduction.
As reduction. Both of them are written as reduction. How do you know? This aluminum is in +3 state, but here is in 0 state. Iron is in +2 state, and here it is 0 state. So it is written as reduction. But from the cell notation, you can tell which is the oxidation and which is the reduction. From the cell notation, you know that your anode comes first and oxidation takes place in the anode. After this double slash, which is the salt bridge, is your cathode, which is reduction. You can also see it from the species that is coming first. Here you have aluminum, which is in the 0 state, going to +3, that is oxidation. And here you have Fe2 plus going to Fe, which is in 0 state. So it means this is reduction. So now that you've been able to tell which is reduction and which is oxidation, if you have this kind of equation, straightforward, without even balancing the equation, you can get your answer. If you decide to use your E naught cell is equal to the E naught on the right minus the E naught on the left, right minus left, reduction minus oxidation. Remember, I said for you to remember whether it is right or left, just remember redox. Red come before ox. So it is reduction minus oxidation, which is your right minus left. If you decide to do that, your right minus left here would be what? From this question that you have on your slide, your right minus left would be what?
Minus 0.41.
Minus 1.
So if you're saying that your E naught cell is equal to E naught, either you say right or you say cathode. Cathode minus E naught anode. Either you say that or you say E naught right minus E, or you say E naught right minus E naught left is the same. If you have identified which is your cathode, which is the Fe, so this is equal to Fe. What's the E naught value for the cathode?
Minus 0.4.
Minus and then minus 1.66. Everything is in volts. What does this give us?
1.25.
Plus 1.25.
Plus 1.25, right? So you may want to put
Yes,
particular. So that way you have your answer already. Very straightforward. Very straightforward. If you can just identify which is anode and which is cathode. But if you decide to now go through the E naught is equal to reduction potential of the cathode minus plus oxidation potential of the cathode, then you have to go through the process. So we have this on the slide. What you have is aluminum 3+ going to aluminum, 0 state. The first thing you need to do is to identify which is your oxidation and which is the reduction. Now on this slide, you can see that your oxidation has been given as aluminum, and they've rearranged the equation as it should be in oxidation, because this is oxidation. So this has been identified, and then you have your reduction as it is. Once you have done this, you then want to balance this equation. You want to balance this. In this other question too, you may want to balance the equation depending on how the question is asked. Depending on how the question is asked, you may also want to balance the equation. But for this, you don't have to balance the equation. And for this question, you really don't have to balance the equation for you to get your E naught value. And this is because your number of moles of the electron does not affect your E naught value. So if you're able to identify what number of electrons is involved in the reaction, it doesn't change the E naught value. All you just need to say is, okay, this is E naught right minus E naught left, or reduction potential plus oxidation potential. You will get the same value irrespective, but your equation may not be balanced. And if the question expects you to balance that equation, you have to balance the equation. So it's good practice for you to just balance the equation, because you can even be asked to give the redox equation, because the equation has been given as 2 half cells. So you may be asked to give us, and I think that's probably how the question would appear, that, okay, give us the full equation of these 2 half cells and tell us what the E naught cell is. So for this this equation has been arranged as oxidation reaction and your reduction reaction. So you can see that your number of electrons is not balanced. Every other thing is balanced except the number of electrons for you to combine this. Okay, another thing I want you to see is, in this case, you would add up the 2 equations like you would do in your redox when you are balancing redox equation. So what you do in redox equation is you add the 2 together, isn't it? Let's finish this example, right? When you add these 2 together, before you add it together, you make sure these electrons are balanced. So for your equation 1, you multiply by what?
By 2.
By 2, fantastic. And then your second equation, you multiply by 3, just to make sure that the equation, yes, just to make sure that the equation is balanced. Once the number of electron is balanced, you can then add the 2 equations together. And this is what you would have if you do that. So we have multiplied here. You have your 6 electrons and 6 electrons. By the time we add these 2 equations together, this 6 electron will go out. And then what you would have left is 2 aluminum. The final equation would then be 2 aluminum plus 3 Fe2 plus to give 2 aluminum plus 3 Fa2 plus. And remember here, from this point, because this equation was reversed, it was originally written as oxidant plus number of electrons to give the reductants. But now this has been rearranged. At the point where this was rearranged, the value changed. Let me take you back there. This was the equation that was given. this equation here was given. Because you want to arrange it as oxidation, you have reversed it. Can you notice the difference in the what we call it now? In the value. Now it's the negative value of the standard electrode potential. This is because this was rearranged, because you want to add the two equations. As a matter of fact, let's finish this. So when you do this, before I take you back to the first one, when you do this, you can then add the two equations together. When you add these two equations, you also add the E naught value. So what you have from here is equation 1 plus equation 2. So you have 2 aluminum plus 3 iron. This 6 electron has gone out to give 2 aluminum 3 plus 3 Fe, and then you can add the two. Notice that when we multiply the first equation by 2, this value is still the same. We didn't multiply it by the number of electrons or by the value with which we used to balance the number of electrons. So this is 1.25 like we got. Now let's look at if we want to say E cathode minus E anode. Let me take it back to the board. In this equation, this was added, remember, just like you do with your normal redox reaction. Now let's assume you don't want to change it. You want to leave it as it was given. So this was the way oh, sorry, I want to confirm something. You can see both my slide and my board, isn't it? Can you see both?
Yes, ma'am.
Okay, fantastic.
Yes,
so you have it, and we don't want to use, because I want us to stick to one so that we'll not be confused. This is very short and very straightforward if you're going to do this, and the possibility of you making mistake is minimal. As long, even from this, even from here, from this, you can tell what your E naught cell would be, because now you know this is cathode, this is anode. So you just go cathode minus anode. So you say this value for Fe minus 0.141 minus 1. And you get your answer. But I want to show you why the two are the same. Either you use addition if you reverse this to oxidation, or if you use subtraction if it is in reduced form, because subsequently we will stick to this way of writing cell reaction. So it's better I make you understand that. I know that a lot of you are used to adding 2 half cells at when you're balancing your reaction. So you have the first equation to be aluminum 3 plus 3 electron to give aluminum. And then the second one, you have Fe 2 plus 2 electron to give Fe. So this is 1, and this is equation 2. And we say that your aluminum is the anode, right? And this is the cathode. Anode and cathode. Let me move my laptop so you can see the end of the board. Okay. And we want to use this formula and also make sure that this equation is balanced. We want to get the final redox equation for these 2 half cells. For us to balance this, we need to multiply equation 1 by 2, this by 3. Please, I hope everybody can understand. If you do not understand, pick up your year 1 notes, please. Just make, it's not hard. It might look tedious, but it's not hard. The moment you get it, it's very interesting. So multiply by 2. So this is 2Al 3 plus 6 electron to give 2Al. And that's aluminum. And this is 3Fe 2 plus 6 electron to give 3Fe. Remember that we are saying that this is anode and this is cathode. And we are saying it is cathode minus anode. So that means the equation, this is 3, 4. Cathode minus anode, that's equation 4 minus, let me write it out before you think it is dash, minus equation 3. So you go 3Fe 2 plus plus 6 electron minus 2, right? I'm intentionally writing it out like you would do in mathematics, minus 6 electron to give your cathode 3 Fe minus 2 aluminum. Now from here, you can see your electron is going out with this. So what you have is 3 Fe. We are going to collect like times and make sure what we have is positive. This is minus, this is minus. So we'll leave it out. Sorry, you can't see my board. This is minus and this is minus. We'll leave it out because we want to take it to the other side to make it positive. There is a negative there that we want to bring to this side. There's a negative there. Can you see the negative? Minus 2 aluminum, right?
Yes.
All right, so we bring that one here, plus 2 aluminum, and then what we have is 3 Fe plus 2 aluminum 3 plus. So you see that this is the same thing as saying 1 plus 2, equation 1 plus 2. So as a matter of fact, what is actually happening there, why we have to reverse your value of oxidation potential, like I explained earlier, is that reduction potential, it's called reduction potential, is given as a reduction cell reaction. So if you're saying,
Please, can you see the board?
You want to see the board?
The board, yes. Okay.
So if you want to use it as an oxidation, you have to make it negative of the value that you were given originally. So whichever suits your fancy, please use, but understand both. So whichever comes your way, you know what is happening. I hope you understand what I'm trying to explain.
Yes, ma'am.
Okay, good. All right, so here, your minus 1.66 has changed to plus 1.66 here because this has been written as an oxidation reaction. And therefore, at the final stage, you are going to add the two together, reduction plus oxidation. But if you want to use it as reduction, you leave the value as it is, and you would say cathode minus anode. You would need this equation. So please go back now, practice it. By the time we talk about different types of electrode, we'll come back to it, but we'll just rush through it. I will just be willing to take your questions at that point. Okay, so your relationship between equilibrium constants and E0 cell. Relationship between E0 cell and your equilibrium constants. The sum of the most important results from electrochemistry are the relationships among E0 cell, Gibbs free energy, and equilibrium constants. E0 cell, Gibbs free energy, and equilibrium constants. So the measurement of your E0 cell gives you, are you done with the board?
No, ma.
It is well. This small thing. Okay, the measurement of cell EMFs gives you yet another way of calculating equilibrium constants. Combining several equations, we would obtain E0 cell is equal to 2.303 RT over NF log K. Now you remember where we started from when we were talking about chemical potential and electrical potential, and then we proved, and then we went all the way down. If you remember, we got to the point where we showed the next equation, right? We got the very first class we had. We got to the point, oh, we haven't gotten there. We haven't gotten there, but we got to the point where we have our electrochemical potential. Okay. We got to the point where we have our electrochemical potential. So your E0 cell is equal to 2.303 RT over NF. How we arrived at this equation, we'll show it shortly when we start talking about electrode, and we'll start with the standard hydrogen electrode. Okay, but take note of this equation. It's really important. So every other values here are constants. So your R is your gas constant, your T is your temperature, and since we're talking about standard cell EMF, we'll be talking about standard states too. So you have your gas constant, you have your temperature, you have your Faraday constant. Your temperature at standard condition is 25 degrees Celsius. So it is a constant. By the time you enter in the values for all of these, it's going to give you 0.5915. All this constant here, by the time you enter their values and you solve, what you're going to get is 0.0592. And then you can substitute that into the equation to give you 0.0592 divided by n log K. Log K. So this is what you have as your EMF, your standard EMF of the cell. So you have your N, which is number of electrons transferred in the balanced equation, where your K is your equilibrium constant. Some equations will substitute this K with Q. This is also very similar to your equilibrium constant. So all you just need is to use the activity of the ions, which is also very close, which is assumed to be the concentration of the ions in solution of the products divided by that of the reactant, as you have here. So your K, you remember your K from your equilibrium constant to be the concentration of your product divided by the concentration of the reactant. This, can't see this. Can you see what is on that slide? My control. Okay, so previously we determined the standard EMF for the following cell. So this cell, from our previous example on slide 30, we determined the EMF for this cell. That's the very first example. So zinc, again, zinc is your anode, isn't it? Zinc, okay, don't let me allow you to talk. Zinc is your anode and copper is your cathode. So in the anode, what we have is oxidation. So you have your oxidation moving to reduction. By a glance, you should be able to tell these things. Okay, so the final equation for this, you have it right there, which is zinc plus copper 2 plus to give your zinc 2 plus and your copper. Calculate the equilibrium constant for the reaction. So from the equation that you are given, A naught cell is equal to 0.0592 n log K over n. From this equation, what's the number of electrons? Please, can anyone tell me the number of electrons from this equation?
2.
2, fantastic. So all you just need to do is to say your A naught cell, which has been given to be 1.10, and then 0.0592 divided by 2 log K. When you solve this, you divide the A naught cell with the value and find the antilog of that value. If you do that, your final answer should be 37.2. Should be 37, the log K is 37.2, and then the antilog of K is 2 times 10 raised to power 37. And that is the equilibrium constant for that. I wish I can give you a question to solve quickly. Let me see if I have that at the tip of my finger. So I'll just give you the question to solve. If it doesn't have. All right, let me just move on. I want to see if it doesn't have more than what we've covered so far. Okay, so your dependence of EMF, I can move this away from the board now, right? Your dependence.
Yes.
Thank you. Your dependence of EMF on concentration. Recall that everything we have done so far has been with a standard cell. Everything we've talked about are on standard cell, but we can also relate this with a cell that is not a standard condition. All you need to introduce is a conversion factor. So you have, if an electrode is a measure of the extent to which concentration in a half cell differs from an equilibrium value, then concentration will affect equilibrium and vary electrode potential. Electrode potential is dependent on concentration. Further from equilibrium, you would have greater potential. Remember, the E on the table is for standard conditions. If concentrations are not standard concentrations, then the cell potential must be corrected. Basically, the potential for non-standard cell will be equal to the standard cell potential with a correcting factor for non-standard concentration. And the equation is this. Your E cell, which is now the EMF of the new cell, which is not at standard condition, is the standard cell EMF with a correction factor, which is minus 2.303 RTNF log Q. All this we'll talk about how we arrived at this equation. We quickly go through it in our subsequent class, but this is the next equation for non-standard state cell. So when you have a cell that is not in its standard state, this is the E value. This is the equation you use for E value. Remember that your E naught value is also similar to this, right? If you remember the equation I showed previously, your E naught value was 2.303 RT over 2.303 RT over NF log K. Before we found all this, because it's a standard state, the T was at 25 degrees centigrade, and we know the gas state and the Faraday constant. So by the time we calculated this, what we had was 0.05915, which is 0.0592. So the only correction factor is similar to the equation you have for your E naught cell, but is E naught cell minus this. Okay, so that's your next equation. There was something I wanted to write on the board when we talked about this relationship. Yes, it says some of the most important results from electrochemistry are the E naught cell. Let me take this.
Here is the lineup. And I think
so what we have, let's say K delta G naught and E naught cell. You have your equilibrium constants, you have your delta G naught and your E naught cell. These are the most important constants or values that you can get from electrochemistry. And there is a relationship between the three of them. No, let me not write it down. So what you have is, and then you have this. Now I want you to just keep this as a cheat sheet. You know that your delta G, the relationship between your delta G and your K is delta G naught is equal to minus RT in K.
No, we are not seeing the board.
Okay. It should be better now. So you have your delta G naught. The relation between your delta G and K is delta G naught is equal to minus RT ln K. Somebody has unmuted again. And then your E naught cell and your K. E naught cell is equal to RT over NF. So you can say E naught cell is equal to RT over NF ln K. That's the relationship between your equilibrium constant and your E naught cell. And when you're looking at the relationship between your delta G naught and your E naught cell, is delta G naught is equal to minus NF E naught cell. So this relationship as it is, just keep it as a cheat sheet. So you remember the major relationships between your E naught cell, that's the EMF of the standard cell, your delta G naught, and your equilibrium constant. So today, we want to start with a standard electrode potential. We want to talk about the standard electrode potential. Remember that your standard electrode potential is that table that you have from your, okay, I think I can stop sharing now.
Sorry, E naught equals RT over NF ln what? We can't see that side.
Ln K.
Ln, okay.
In K.
Okay, so I think you would even understand my view. All right. So as I was saying, we're going to start a standard. Let's talk about the standard electrode potential, the standard hydrogen electrode, and then we'll talk about different types of electrode. And then you see why we need to, how we arrived at all of these equations that we have looked at earlier. So your standard electrode potential is measured relative to that of the standard hydrogen electrode. So remember that I told you that that table, the reduction, the standard electrode potential is a reference to the standard hydrogen electrode. So standard hydrogen electrode is used as a reference for every other cell. So you see on that table that the standard hydrogen electrode, the electrode potential for hydrogen is 0. Please, if you have that table, please bring it out. Mine is on a hard copy here. Please, that table, I want you to view it and just follow me. On that table, you would see that hydrogen is 0. The value, the EMF, the cell potential for hydrogen is 0, correct? So every other cell is measured relative to hydrogen. So what you have is the standard hydrogen, the standard electrode potential of an electrode is measured relative to that of the standard hydrogen electrode. Now, the standard hydrogen electrode is as shown. What you have in a standard hydrogen electrode is you have a beaker and a solution of concentrated acid. Usually, okay, my body. So what you have, you are asked to draw a standard hydrogen electrode. What you have is your beaker containing, so here is containing, I need to put that there. So all this is your acid solution, usually your HCl. So acid solution. Hope you can see this on the board. So what you have is your solution, and then you have a platinum sheet suspended in this solution with a platinum wire. So here you have your platinum wire, and then this is your platinum sheet. So you have hydrogen gas. You have hydrogen gas being, passed. So this is hydrogen gas, pure hydrogen gas being passed into that sheet containing on the platinum sheet. So this is covered this way. A glass tube. So this is your glass tube. I think this is all the components you need in your, so you have a platinum sheet, you have pure hydrogen gas being passed over this platinum sheet. So you have your gas being in contact with the platinum. So you have your gas in contact with the platinum. This is platinum sheet suspended by a platinum wire. That is what you have in your standard hydrogen electrode. So here, you say that your standard hydrogen electrode is shown, and it consists of a purified hydrogen gas, which is passed over a platinum sheet that is attached to a platinum wire, immersed in a solution of hydrogen chloride. This solution is to provide the acidic medium that is needed, because for reduction to occur, for oxidation to occur, you need your acidic solution. So it is immersed in a solution of 1.0 mole per dm cube hydrochloric acid. The standard hydrogen electrode involves equilibrium established on the surface of the platinum between the hydrozonium ions from a solution in which they are at unit activity, and hydrogen molecules from the gaseous state, and a pressure of 1 bar. So your standard hydrogen, that's why it is called standard. It's an hydrogen electrode, but it is kept at a standard state. And the standard state has been stated to be a pressure of 1 bar at 25 degrees Celsius. The equilibrium reaction will produce a potential on the metal surface. As your platinum is the metal, on the metal surface, but this potential is arbitrarily taken to 0. The potential is arbitrarily taken to 0, and the equilibrium that is attained at the surface of the platinum is written as H plus. So you have your H plus. If this gains electron, it will be reduced to H2 gas. So because this is 1 and this is 1, so what you have here is half H2. This can be, it's an equilibrium. I hope you can see my board. It's an equilibrium. So this can be alternatively written as 2H plus 2 electrons to give H2 gas. So this is gas and this is aqueous. My board, it's a makeshift, so it keeps moving around. I hope you can see the board. All right, this can be written as H plus E half H2, or you can alternatively write it like this. How this derivation, I would leave it out because you already have this. You already have this in your notes. So if you open to your notes, the notes that you all have, I'm sure you didn't print it out. And I would advise that you print it out. It makes reading it easier. Okay, let me look for that so you can follow me. So go to your page 3 on that notes. Page 3 on the notes. to page 4 and page 5, you see the derivation, how we worked it all out until we get to the potential of the hydrogen electrode. The potential of the hydrogen electrode, which you will find on page 5, equation 6.22. Equation 6.22. So I'm just going to list this out. I wouldn't be proving it. So here, what you have is you write your, okay, let me write this up. I don't want to write this to save. Oh, I hope you got that. But if you didn't get it, it's also in your notes. You need to learn the diagram of the hydrogen electrode. It's very important and it's very simple. You just need about 5 items. You need your platinum sheet, you need your platinum wire, you need your hydrogen gas, you need your hydrochloric acid solution, and of course the glass tube. So once you have that in a beaker and you put everything where they're supposed to be, you have your standard hydrogen electrode all sorted. Please. All right, so when you have your equation as it is written, my marker, your hydrogen, so you have your H plus electron half H2. If you want to write this in terms of their electrochemical potential, in terms of the electrochemical potential, you will have to find the electrochemical, if you remember this from the last class, electrochemical potential of the hydrogen ion plus the electrochemical potential of the electron, and of course, the electrochemical potential, and that will be half the electrochemical potential of the hydrogen gas. Now, all those relationships we used in the class the other time will come to play again here. So if you remember your equation 3A and 3B, so please refer to your notes because some of these, okay, let me explain to you. When we treated it in class, I tried to break down some of these equations that are in the notes so that you understand where those things are coming from. So for you to understand what I mean by my equation 3A and 3B, you have to go back to that particular note to know which of them is stated as equation 3A and 3B. But from equation 3A and 3B, ions in aqueous solution and neutral species. So for ions in aqueous solution and neutral species, the electrochemical potential is the same thing as their chemical potential. So what you have is your mu naught H plus is equal to mu H plus, and your mu bar H2 is equal to mu H2. Both of them are equal. So if you want to rewrite your, this is equation from where we stopped, I think this is equation 11 now, right? So if you want to rewrite this, what you have in equation 11, since this is equal to this, so you substitute with this. So what you have is your H plus, not mu bar anymore. Let me rub off this. What you have is mu H plus, right? I'm taking it from here, plus I'm substituting what you have here, there, plus mu bar electron to give or equal to, so at this point we can use equal to mu, half mu H2, half mu H2. So that's what we have. And let's say this is equation 12A. So we have equation 11, we have equation 12A. Now from equation 5, and what is our equation 5 from the very first class? Our equation 5 from the very first class talk about the electrochemical potential of an electron, which is equal to minus FV, or you say, let me say minus FV, equal to minus F and potential, right? FV. So that's your equation 5. That's a reminder. You can take it from the last class. So, and generally, you know that the general equation we had at the beginning of the class was mu is equal to mu naught plus RT mean A. This is at standard condition, and then this is your correction factor. That's mu naught is equal to RT ln A. Therefore, you can write out your mu H plus. So if you want to break everything down, your mu H plus will also be equal to mu naught H plus RT ln A H plus. Let's say this is 1. You write that out too for mu H2. So your half mu H2, please just follow me. Don't let this bore you out. We are trying to work out how we got our next equation that we'll be using to calculate the EMF of the cell. So this is where we got our E naught value. Remember, we said that our E cell electromotive force of the cell is equal to E naught cell minus the correction factor. So this is where all those came out from. Now, half mu H2, if you write it out in terms of this general equation, what you are going to have is half into brackets mu naught H2 plus RT, sorry, mu naught H2.
Wow, we can't see the board.
You can't see it. Oh, this is my board there. Is it better now? Is it better now?
Yes, ma'am.
Okay, so that will now be equal to
Please,
mu naught.
please mute your mic, please.
Thank you. Mu naught plus RT ln the fugacity of H2. So rather than put a bracket, or let me just leave it like that, plus RT ln, because this is in gas, so we use fugacity and not activity of the ions. This is gas, so we use RT ln FH2, where your A is the activity of the ion. So this A here, AH plus, is the activity of the hydrogen ion in aqueous solution, and F is the fugacity of the hydrogen gas. Now, if you decide to substitute equation 1 and 2 into, no, equation 1, 2, and 5. Remember, we are trying to substitute mu electron, electrochemical potential of the electron, the chemical potential of the hydrogen ion and the hydrogen gas into equation 12a. So before I rub the down part off, I need to open this up so you can see the top of the board. Sorry but everything in this has been written in your notes. It's just that I may have 1 or 2 additional steps to make you understand, but everything is in your notes. All right, so if we decide to substitute equation 5, 1, and 2. So equation 5 is mu electron is equal to minus Fe, but that's not where we are starting from. Equation 6 says mu H plus, so we're going to mu not H, so mu H plus, yeah, we have mu H plus as equation 1. So instead of us using mu H plus, we're going to use the mu naught H plus plus RT. So we have mu naught H plus RT ln A H plus. That's for that, which is then plus, then it comes here to say plus mu naught electron. It says plus. So your mu naught electron is minus FV. So I say minus FV. That's the potential of the hydrogen ion to hydrogen gas. So I need to put that as a subscript. And then the next thing here, you don't understand what?
I don't understand how you got this mu naught H plus RT ln A H plus.
Okay, I said that from equation 12a. From equation 12a that I wrote earlier, I reminded you of a general equation that your nu naught, your nu is equal to nu naught plus RT ln A. A chemical potential is the chemical potential of the standard plus RT ln A. It's a general equation that you have come across at some point when Dr. Kibulu was teaching you. And it's also in your note. I think it's equation 1.1. If you check the note again, it's equation 1.1. That equation, that is there. That equation is there. So if you write it in terms of, please mute your mic after speaking to reduce background noise. Thank you. Dosumo, your mic is here to be muted. Let me just mute from, okay, good. Thank you. So your new here, if you substitute what you have from that equation 1, the very first equation, that general equation, mu is equal to mu naught plus RT in A. Now, wherever you find mu H plus, you substitute it with mu naught plus RT ln. Because it is for H plus, you have to put the subscript indicating that this is for H ion, that's hydrogen ion. And then anywhere you find mu H2, you also substitute it with mu naught H2 plus RT ln. But because hydrogen gas is a gas and not a ion, we are using fugacity and not activity, because activity goes with the activity of the ions in the solution. Activity of the ions in the solution. Meanwhile, gas, you are either talking about its fugacity or you talk about its pressure. So if you use that equation, and this equation 5, this one we treated it the very first time. I don't know if you were in class that day, our very first class, that was when we got to this equation 5. So you substitute your electrochemical potential for the electron. Instead of you using mu naught electrochemical potential of the electron, which is mu bar of the electron, you use minus FV. So if you substitute equation 5, equation 1, and equation 2 into this equation 12a where we have, what you are going to have is the mu naught. That's where we have mu naught. I hope you can see the top of the board. Mu naught of the hydrogen ion plus RT ln. Sorry, I need to pin this to a wall. All right, so the mu naught of the hydrogen ion plus the RT ln activity of the ion minus FV, which is the electrochemical potential for the electron. So instead of us using this nu, we are using minus FV, which is the Faraday constant and the potential of the electron. So equal to half H2. Again, your H2, we're going to substitute it with mu naught H2, so which is equal to half. Your mu H2 is now mu naught. Oh, I need to get up. So your H2 is now, I hope you can see this. Your H2 is now.
You can't see the upper part.
You can't see the upper part.
You can't see the upper part of the board.
You can see it. Can you see it?
Yes, now we can.
Okay. So this is now going to be half mu naught H2 plus half RT. So we are substituting this. So half mu naught H2 plus half RT ln the fugacity. Ln the fugacity of hydrogen ion. So here we want to collect all the like terms. So you have minus F.
And we can't.
Can you see it now?
No. Yes, ma, you can see it now.
I'm going to move it shortly, so please hurry up. I hope you're done. Are you done?
Yes, ma.
All right, so we want to collect these like terms. Want to collect the like terms. So you have, we are leaving only minus FV on this side. Minus FV, that's H plus H2. That's this is now the voltage moving from your hydrogen ion to your, when you have that reaction. when you have that reduction reaction, the potential associated with it. So this goes to the other side. So what you are going to have, if you collect that like term, is you already have your half mu naught H2 on this side plus half RT lane plus half RT lane fugacity of H2 minus mu naught H plus minus RT lane activity of H plus lane activity of H plus. So here we are just going to keep collecting the like terms. We're going to bring the mu naught A plus minus half RT and then minus half RT lane A. We want to collect the like time. So we are bringing the mu naught together. So this is mu naught and this is mu naught. So what we're going to have is half mu naught H2 minus mu naught H plus is it plus or minus now, which is convenient for us. So plus, let me use minus. So what you have is minus ln of the minus RT. So let's bring out, because RT is common to both, minus RT. Now, ln fugacity, what's the, where do we have here? Half mu naught H2. What we want to make this mu naught H plus positive. Okay, anyway, we can multiply by half much later because we want mu naught to remain as positive. Okay, let me just move on. Minus RT. So ln, this is out and RT is out. So what we have is ln fugacity of H2 minus of, no, this is plus ln activity of H plus. I hope this is correct. Yes.
Please help us adjust your.
Is it okay now?
I can't see it. Though.
I still can't see the right side.
Okay, is it okay now?
Sorry, my just the ending part. The
Okay,
last
can you
part,
see
the
this
lean
ending
something.
part? It's better now.
Yeah, we can now. Yes, ma'am.
Okay, so I said that I want this mu naught H plus to be positive because I want it as, so I want to multiply this all through with minus. So this is minus half. The arrangement that I want this.
Please, what of the RT before the ln A?
It's
H
here. So
plus.
there's a bracket here. Thank you.
And so if there's a bracket, meant to be minus.
Minus RT lane F. See, this is minus RT lane. Okay, this is plus and this is minus. Is that what you're saying?
Yes, ma'am. No, ma'am. This is minus and minus.
This is half RT lane F. So this is plus RT, right? And this would be
There's
minus.
minus there.
Right? Now, please, I want you to take note of this half here. This half has come here. You know, this is also the same thing. This lane fugacity H2, half raised to power half, is the same thing as half lane from mathematics, right? Do you understand what happened there?
Yes, ma. Indices.
Indices, thank you. All right, so I want to make my mu naught H plus positive. So I want to multiply this through by minus. So it's minus right here. What I could have done here is to collect these terms such that this is mu naught H plus. This comes here and this goes the other way. So what I'm doing now is this minus, I'm taking it to this side. So instead of minus FV, this is FV, right? So I'm dividing it through by negative. I hope you understand. So this will become mu naught H plus minus RT ln F half H2 minus ln, that's F half H2 minus ln AH plus, right? Right? Because this minus is only applicable to all of this. This is brackets. So once we have this equal to mu naught H plus minus half mu naught H2, right? Mu naught H2. This has been taken care of. Minus RT ln, ln. I'm also bringing out the ln. Ln is common to both. So this is going to be what? Mathematics. Do I have anybody in the house?
Division.
Thank you. Divided by H plus. So we want to divide both sides. Please always remember your cell. This is an hydrogen, for an hydrogen cell. So your V bar, your VH plus H2. So what you have now is, I'm leaving just your potential, H plus H2. I'm dividing through by F. So this is going to be mu naught H plus minus half mu naught H2 divided by F, right? Minus RT over F ln F.
Ma, we cancel the board, ma.
Oh, that's better now. F ln H2. Let me move this up a bit so it doesn't confuse you. F half H2 over AH plus. So this is F half H2 over AH plus. If fugacity, now because we are talking about standard states now, you know, this is an hydrogen electrode. This is the potential for hydrogen electrode. So at standard states, fugacity of the hydrogen gas, what you have here, would be 1. And the activity of the hydrogen ion, which is AH plus here, I hope you can see it. The activity here of the AH plus will be 1 for standard states. So if you are saying that we are looking at the standard state of the hydrogen electrode, your fugacity is 1, activity of the hydrogen ion 2 is 1, then the potential is in standard state. If that be the case, the equation becomes, let me take it up because this would now be too low. I want to take this up, but I'm moving from this down. Remember the last, for standard state, this will be 1, this will be 1. So that would be ln 1 over 1. And ln 1 is what? Ln 1 is what?
0.
Thank you.
0.
So maybe I should not even disturb myself. So you know ln 1 is 0. So we say at standard state, please remember. At standard state, fugacity of hydrogen is equal to 1 and activity of hydrogen plus is equal to 1. So V naught, you have to put the naught of this hydrogen electrode, H plus H2, is equal to mu naught H plus minus half. Oh, sorry. You didn't tell me. Sorry, I was already writing. Okay, so mu naught H plus minus half, from the lower part, minus half mu naught H2 over F minus RT times, minus RT over F times 0 is going to be 0. So that's all you have. This becomes your equation. I even lost count of my equation, but it's still equation 12. Let's say equation 12D. So this right here is your equation 12D. Equation 12D. So also remember that the potential, the chemical potential of an ion from our previous derivations, chemical potential of an ion and the chemical potential of a gas of a species in its gaseous state is equal to 0. So the chemical potential of a species in its gaseous state is 0. Therefore, this constant here would be 0. So if that be the case, your standard potential of the hydrogen electrode will be equal to mu naught H plus over F. This is your equation 12E. Let me leave it as 12E. Now, if you substitute equation 12D, this equation here, equation 12D into equation 12E. So what you are trying to do is, instead of you saying V naught H plus here, you are substituting V naught H plus minus half mu naught H over F into this equation is equal to your mu naught H plus. You would have equation 13. So you are substituting equation 12D into equation 12C, and I've rubbed off equation 12C. But from your notes, your equation 12C is that point we got to before we talked about standard state. Please, you remember the equation before we talked about standard state? Can anyone read it out for me, please? Let me charge my battery. Can anyone read it out for me, please? The equation before we talked about standard state.
Mu naught H plus minus half mu naught.
Sorry, you're not clear. Sorry, you're not clear.
Mu naught H plus.
Mu naught
H plus.
Can somebody else read it out?
H2 over F.
Mu naught H plus.
I'm listening.
Mu naught H plus minus half mu naught H all over F minus RT over F.
Thank you.
Leave F.
Thank you very much. So what we are doing is we are substituting equation 12D and 12E. So where you have V naught H plus, where you have this V naught, when you have V naught, where you have mu naught H plus minus half H2 over F, you are going to substitute this value here for that value. If you remember, we said VH plus H2 is equal to the whole of that, the whole of this minus RT over F lane F half. So in this equation here, we're going to say V naught standard, and then this one that you have here, you will write it for that one. So you substitute it with this, which is V naught H plus H2. So here, if you substitute this, remember this is V naught, and that is VH plus. Then your VH plus is mu naught H plus minus half mu naught. So instead of you writing this there, you are going to write this standard one here, V naught. So this is equal to V naught H plus H2. So that equation you read out was the whole of this minus RT over F lane F half over AH plus. So I'm going to write it minus RT over F lane F, that's fugacity of the hydrogen over activity of the hydrogen plus. So here is your standard, is the standard EMF, the standard potential of the hydrogen. And this right here is the next equation when you don't have it at standard states. this right here is what we call our Nernst equation. So if you look at this closely, you can say your E equals to E naught minus whatever it is you want to put at the back. So we can say this is equation 13. Equation 13. Equation 13 is the next equation for the hydrogen electrode. So generally, your next equation is V equals to V naught minus RT over F. Remember that RT over NF is because N for hydrogen is, what do we call it? Hydrogen is 1, electron for hydrogen is 1. So over NF or 2F lane activity of the product over activity of reactant. If you remember what we have done today, something like this is similar to it, where we use that of equilibrium constant. Remember that at for ideal states, your equilibrium constant. For ideal states, your equilibrium constant is the same thing, it's very close. So you can as well say it's the same thing as the activity of the ions. Oh, I hope we can cover so much. So I have some class exercise. I'm going to rub this off and quickly write the class exercise.
Please, can
I do what?
adjust your can you please adjust your system so we'll see a wider?
Okay, maybe I should move it back. I think that is going to help. This has refused to stand. Maybe if I moved it back, you may see a wider view, truly. I never even thought of it. It's quite better. So I want you to write, oh God, give me a minute, please.
Hear you.
Hello, Mal.
We can't.
We can't hear you. People don't apologies, please. Oh, apologies. So where are we? Is it better now, or you need me to raise it up a bit? Hello, can you hear me? Hello? Can you hear me? Hello? Okay, can you hear me? All right,